Sorry, Gisela, you're maybe muted.
Thank you. Well, I was basically speaking in the void.
Yeah.
Okay. So welcome back. What I was explaining is in big data, we never delete or insert or replace anything. We just keep adding new versions, just like in GitHub. And so when we look at what's happening here, we just keep creating new key values. These are the ones that were created recently. This was flushed a long time ago. This is older, and this more recently. And then when you read a row, the user might want to read the entire, all of the row, maybe 20 or 100 values. Maybe the first columns in that row were modified very recently, in which case you will be interested in those in the memory. But maybe the column 3 and 4 were very old and they haven't been touched in like a year. And then you need to look here. So this is the reason why you need to look everywhere. If you only look in the memory, then you might be missing some older values, right? So you need to look absolutely everywhere. But it is true for those of you who said in memory first, that if there are multiple versions, maybe the same data has version 1 and 2 here and version 3 here and version 4 here, then indeed the latest version wins. And then this one takes precedence over the others. So who agrees with me? We need to look everywhere, right? Absolutely fundamental. So we look everywhere and then we return all of the key values to the user, possibly trimming the versions that are not the latest versions, but that's it. Okay. Now, let me go to the next problem. I keep saying there's a problem and then here's the solution. So here's the next problem. Imagine now that we keep using HBase over a very long period. So the memory is full, we flush, the memory is full, we flush, the memory is full, we flush. Does anybody see the problem coming? At some point, I'm going to end up with 100 H files, with 1,000 H files, with 1,000,000 H files. But I have to look everywhere. So do you see the problem? We have to look everywhere, but we might have a huge number of H files now. So this is just impractical, right? We can just keep flushing and flushing and flushing. So we need to do something more than just flush. And so the answer to this is when we start having too many H files, we start merging them. And that is called a compaction. So imagine now for my slides, I was not going to put too many of them. So let's say I have 3 H files. And then I decide these are too many H files. So I'm going to merge them into the same H files. So I take them and I merge them into one single bigger H file with still the order of the key values. What do you think is the algorithmic complexity of doing that? Is it n log n because I need to sort the key values, or what do you think? What's the complexity of doing that compaction? Who thinks it's n log n? Nobody. Who thinks it's linear? Yeah, it's linear, absolutely. Because all we need to do is go in parallel through the 3 files at the same time, because they're already ordered. This is already ordered, this is already ordered, and this is already ordered. So I just do a traversal of the 3 files, and I keep taking the smaller values and then write to the H file. So this is in linear time, very efficient. Who ever heard of merge sort? A sorting algorithm? Some of you. This is basically the second half of merge sort, right? In merge sort, you first sort smaller amounts of data and then you merge. And the second part of the merge sort is when you merge this already sorted list. So this is linear time, very, very efficient. And in big data, we absolutely love linear time. This goes well with clusters. All right. So now that's good because we only have one single H file now. Now we can more efficiently access the key values in there with the index. All right. So this is called compaction. So I summarize, when the memory is full, we flush. And when we have too many H files, we compact. It's that simple. So we flush and we compact. Now, to give you a bit of theoretical background with what's going on here, these are 2 very important techniques in database management systems, which are B+ trees and log structured merge trees. B plus trees, we'll actually look at them in details in MongoDB at the end of the semester. B plus trees give us a way to optimize the access to the disk for a database to build indices on for example, relational tables or collections of documents. So this is where you have a system where you have latency issues and you want to make sure that you don't have too much latency. So you basically are going to be bound by latency on these systems. But here we have a different problem with HBase. We have absolutely gigantic amounts of data, and we keep write and modify the data and keep adding more and more and more and more and more and more. And we want to make sure that we optimize the patterns of how the data is written, right? And so the idea of LSM trees, log structured merge trees, it's a tongue twister to pronounce this thing, log structured merge trees. It's simpler than it sounds. I will show you an animation. It's much simpler than it sounds. But the idea is this. You have several levels of data. At level 0, this is the fresh data that is in your memory. At level 1, these are basically the H files that were just flushed from memory. At level 2, these are the ones that were compacted from previously flushed files and so on, and you just get deeper and deeper and deeper, right? So the idea is that this is all what's new. This is the more recent, and then they get larger and larger. So we maintain multiple levels of data based on freshness. And this way of doing things, which is the magic behind HBase that answers the question that I asked at the beginning of the lecture, how can it be so fast in spite of being on HDFS? And this is why. But I think an animation is much better than that, because the animation you will see, you will understand what's going on and how the trick actually works. So I'll drive you through what's happening now over the long term in HBase. I'm looking at a specific store, specific region, specific column family. So we have a fresh HBase, no data in there, and then people start creating data in it and maybe modifying what they've just created and so on. So where does it go? Where do the key values go? At first, they go in memory. Yes, absolutely. Everything that is fresh goes into the memory, always first into the memory. So at first, we don't have anything stored as H files or anything. It's just new, and we just have the mem store, so the memory of the region server that starts filling. At some point, the memory becomes full. So what do? We flush. So we flush. When we flush, we write to HDFS an H file, right? It's going to be relatively small compared to what is to come, because that's just one flush of one full memory. So we have an H file. But the users are not going to stop there. They are going to continue to write and replace and delete and insert and do whatever they want to do. And that is going to create, again, new key values with new versions, and that's going to, again, fill the memory. So the memory is full again. What do? We flush. So we have a second H file similar to the first one, the same size, but with the newer version of the data. So now, let's say, to simplify a little bit, that we decide that 2 is too much. Like 2 H files of the same size is already too much. So if I think that this is too much, what do I do with these 2 H files? I compact, I merge them. It's called compaction. So if I merge these 2 H files in linear time, that's just giving me 1 H file that is just twice as big, right? It's just now double the size. So you see, I do a compaction and get that new H files. Then I can drop the other ones. Okay, who is with me? So flushing, compaction. But the users are still not going to stop here. They are going to keep creating and deleting and modifying and replacing and so on. And that goes all in the... Anybody? Where does it go? Yes, absolutely. Yes, that goes in the log. And after it's in the log, it goes into the memory. Exactly. So we, again, have filled the memory. So what do? The memory is full, so we flush, exactly. We sort, absolutely. The flush also involves sorting. So we keep it sorted and we flush it. Now we have a new H file that again has the original size corresponding to one full memory. So now look at what we have. We have this older H file that is twice the size, and we have this newer H file that is single size, right? So at that point, we have three places to look at when users want to query data: here, here, and here, right? This is just the oldest data, then that's a bit newer, and that's even fresher. So if the users keep using, because they keep using the system, we again fill the memory, so we flush. Then we have a second H file, but it's too much, so we compact. And then we have another H file, but that's again too much. We cannot have two, so we compact again. And now we have a quadruple size H file, right? And then the users continue. So the memory is full again, so we flush again. Do you see where that goes? We just keep building, flushing. So now we have two, so we compact again, and they keep using it. And so you see, it just keeps going and going and going and going. Who played the game 248? That's exactly like it. It's actually one of your predecessors that actually noticed that in the lecture. That's like the 2048 game. That's exactly what it is. You just keep compacting and creating these larger and larger and larger H files. And that is how we maintain a log-structured merge trees. And that is efficient, because that keeps both the number of H files reasonable, but it also keeps the number of times you need to compact reasonable as well, right? So there is a logarithmic aspect to it, because it keeps the size grows exponentially, right? So we don't have to compact too much. And so the idea here is that the fresh data is going to be here, and then the more we go to the right, the older it's going to get. And in fact, if you go long enough, maybe you're going to find data that was created millions of years ago, and maybe even dinosaur fossils at some point, right? So this is a very, very old data that would be in the very large old H files. Okay? Who is with me? Right? So that's it. That's the secret. That is why we are able to have a system that is fast. You can write in a random fashion, in such a way that HDFS is not used in a random fashion. Because in HDFS, imagine you put yourself in the shoes of HDFS. What's going on? We just write big files in one go. And HDFS loves that. Or we append. For the HLog, we append. So we use HDFS in exactly the way that it was meant to be used, while exposing to the user something that feels real time, that you can read and write in real time. That's the magic. And that is called batch processing. Batch processing is really this idea that you accumulate the key values in memory, and you only start writing to the disk when it's full in a single shot. That is the secret. Okay, so that's it. Now, somebody else mentioned in the first hour cache. They asked, is that a cache? Is the mem store here a cache? And I said, no, that's not a cache. Because what is a cache? A cache is a copy of something that would take time to get that is closer to you. So you keep closer to you, and in a way that is fast to access, a copy of something that would be slow to access. But the mem store is not a cache because it's not a copy of anything. It's just the most recent data that there is. It's not copied from anywhere, right? So this is why it's not a cache. If we want to have a cache, we can. But then in that cache, what we would have is copies of stuff that is in the H files. So I could have a cache in my memory that has some of the data in there. And what would I put in the cache? Well, typically, my strategy would be, I'm going to put the data that I access very often. There might be specific regions or specific columns that I keep accessing all the time and all the time and all the time. These I could put a copy of in the cache, right? Then I just look in the cache, and I don't need to look at the H files. So I can have that strategy. Another strategy for the cache is to store what you've recently accessed, with maybe the idea that if you've recently accessed it, it's more likely you're going to access it again than what you haven't accessed in a long time. Right. So this is the idea of a cache. But again, the cache, not to be confused with the mem store. Right? The mem store is the fresh data. The cache is a copy of data that is already persisted in H files. Okay? There are cases where the cache is totally useless. For example, if you go through an entire table and scan, that's one of the 4 kinds of queries, right? You scan through the entire table, the cache is going to be totally useless. Why? Because you access every single key value that you can access, and you only access it once. So the cache is totally useless. Who agrees? Right? So if you really look at the entire table, totally useless. And the other use case where it's totally useless is if the access patterns of the users are totally random, meaning that there is no particular region or column family that users access more often than others. It's just totally random. Then again, a cache is totally useless. So you always need to ask yourself, when is it useful? When is it not useful? But in reality, it actually very often happens that there are certain parts of the table that are frequently accessed. We call them the hotspots, right? So the hotspots are basically these regions and column families that are accessed very frequently, and these are the ones that you might want to cache a little bit. There is another optimization that we can do. It's actually funny because these optimizations are actually quite simple, but they work. They are incredibly efficient. So this optimization here basically addresses the fact that you need to look everywhere. Whenever somebody wants to read, you need to look everywhere. I've had repeated that so many times, I'm sure you will remember, everywhere. But could we avoid looking everywhere? For example, if I'm looking for a very specific row somewhere, very specific row, the user wants to read that, and I need to look at 10 H files. But I know, because of some information that is given to me, that this H file and this H file in this H file certainly do not contain that row. Do you agree? Then I don't need to read them. I can save some time, right? I can skip the H file. That's exactly the optimization. So for example, for each H file, I could keep some information about the key ranges, so the row ranges that are in the file or those that are not in the file. And then all I need to do is look for every H file at the range that they cover. And if what I'm looking for is not in that range, then I just skip the file completely. I only look at the H files in which I might find something, and I skip the H files for which I'm certain not to find anything. Who is with me? Right? Very powerful optimization that's generic in big data. Something related that is still the same idea, that we try to skip the H files for which we know there is nothing interesting. It's called the Bloom filter. Who has already heard of that? So it's a mathematical trick. It's a mathematical trick that gives you a way to test whether or not you will find the data you're looking for in a specific file. But that test is skewed. It's asymmetric. So it might tell you yes or no. And what's interesting is that if it tells you no, then that's for sure. If it tells you no, it's not in there, then you know it's not in there. Absolutely guaranteed. But if it tells you yes, that's actually a maybe. The yes just means it might be in there, it might not be in there, right? So the yes, you're not quite sure, but the no, you're absolutely sure. So it's cute. There's an asymmetric thing here. But since the no is for certain, if the result of that test tells you it's for sure not contained in that file, then you skip it. That's the Bloom filter. And why this asymmetry? It's because if you wanted something that both says for sure no or for sure yes, that would be costly in computations. You would have a lot of compute. But mathematically, if you're fine with the yes being only a maybe, then mathematically you can do it very efficiently. And this is done with hash functions and cryptographic tools. It's basically just some cooking done with hash functions in there. And so what's really nice is that, so this is called the Bloom filter, and the Bloom filter are very, very efficient. Right? So it's almost O of 1 that you immediately know if it's for sure not in an H file. So again, always that trick. Once we have established that, for example, the 3 H files that are in gray for sure do not contain any of the data I'm looking for, then I skip them. Right? This is actually a widely applicable principle on big data. At these scales, what is really costly is reading data from the disk. That is, we'll see for MapReduce, for Spark, this is why we actually go to a cluster of machines. And so how do you optimize reading from disk? Well, you optimize reading from disk by not reading from disk what you don't need. This is the quickest path to optimizing. Try to read as little as you can. Try to know when you don't need to read, and then you just don't read it. Right? That's the idea. Right? It sounds very simple, but it actually works. It's extremely powerful in big data. Okay. All right, I'm actually almost done with HBase. Just have a few more slides. What I wanted to explain also is in HBase, the client kind of needs to know which region servers it needs to speak with, right? In HDFS, you ask the name node, and the name node tells you these are the data nodes you need to speak with. In HBase, the way that the clients know which region servers they need to speak with is done with a special table. It's a special table that is located in a specific region server, but that table has the property of being on a single machine. It's not spread like the other tables all over the cluster, it's on a single machine. So on one of the machines, there is that table that looks exactly like the other HBase table, except that they're on a single machine. And that table contains the whole information about all the regions that there are and which region servers are responsible for what region and so on. It's all in that table. So when a client needs to know which region servers they need to communicate with to look for the data or to write new data, they just look in that table. That's called the meta table. It's called HBase meta. And that's it. And it's located in a specific machine, and everybody knows which machine it is. Right. Who is with me? Right. So this is what we call the bootstrap. This is how they know where you need to look. So basically, the client can connect to the HMaster for creating, deleting, updating tables so that they go to the HMaster. The HMaster will then modify the meta table accordingly. And when a client wants to access, read or write a specific region, they connect to the one region server that has the meta table. Again, everybody knows who this is. And that region server will be able to say, okay, these are the regions and this is the region server in charge. The client might even keep a copy of some of that information so that it doesn't need to always ask the same questions, and it can keep some, it's a cache again because it's a copy, so it can keep a cache of some of that meta table, and then it knows from that information which region server it can access, right? So this is what actually happens, okay? All right. Then you should know that HBase is written in Java, actually, just like HDFS is also written in Java. We see that MapReduce is also written in Java. What if you want to access it from other languages like Python or C or R or whatever language you use? Well, again, it's commonly done by having a REST API. So just like S3 has a REST API, HDFS has a REST API, HBase also has a REST API. And once you have a REST API, it's very straightforward for people to write a library in many languages that actually use the REST API in the background. So the REST API is an enabler for use in many, many other languages than Java. Okay? So you see the REST API is really everywhere. It's a very, very popular way to access databases. No questions so far? Okay. I'm done with the complex stuff, by the way. It's all behind us, the complexity of HBase. Now I want to say something about data locality. In other words, I would like to tell you why it was a good fit to have HBase store and persist the data in HDFS, why they work well together. The idea something I already explained, but again, I will repeat it. I told you that in HDFS, when a client wants to write a file, then the first replica for every block on the file is stored on the same machine as the client, right? You remember that. The first replica, same machine as the client, and then the other replicas are going to be on a different rack, the two on the same different rack. Now, something that when I said it might not have been clear, how does it make sense that the client is on the same machine as a data node, right? And the idea is really that in that case, who is the client? Who is writing to HDFS? Writing to HDFS happens when we flush or when we compact, right? But who is it that flushes or compacts? Which process? Yes, the region server, also on Zoom?
No, there's a follow-up.
Oh, there's a follow-up question. Yes. So let me confirm, yes, it is indeed the region server, and then I take the question.
Yes, so Manuel on Zoom asked, is it the case that we contact the table with metadata, and then we are told to which edge master we have to go? And finally, the edge master tell us which region server is the region desired.
Ah, okay, I see what you mean. It's simpler than that. You do not even need to go to the regions, to the edge master. Because if you look at the meta table that everybody knows where it is, you look at the meta table, you can already infer the region servers who are in charge from the meta table. So it is not necessary to connect to the edge master. For that, you can directly do it as a client, right? So it's more efficient than HDFS, because in HDFS, you really have to go through the name node. Here, you don't need to. You can, by yourself, just figure it out from the region server. Right. Does it answer your question?
So the edge master is only responsible to update the data storage when the updates are made?
Yes, exactly. When you want to create a table, when you want to modify at the metadata level, then the edge master is responsible for that. And the edge master is also responsible for monitoring for the liveliness of the region servers. So if at some point, if a region server dies or doesn't exist anymore, then the edge master will organize the succession. It will make sure that somebody else take over, and it will do that by writing to the meta table and by informing them, right? So it's still in charge of the coordination and synchronization, but some of its work was offloaded to this meta table, because for the people who just want to know which region servers are in charge, now they can do that without communicating with the edge master. Right. Does it make sense? Awesome. All right. Very good. So now we've established that the client who writes to HDFS is the region server. I also told you that the region server is a process that happens to run on the same machines as the data nodes. So you have in your cluster one machine that has the name node and the edge master processes, and maybe you have 1,000 machines that each have a data node process and a region server process. So do you agree that when a region server writes, flushes, or compacts a file to HDFS, because they are on the same machine as a data node, the first replica of every block of that H file is going to be physically stored on the hard drive of that same machine that the region server is on. Who sees that? Right? That's exactly the idea. And so that means, if I look at that machine, where we have the region server process that is handling regions, and we have the data node process that has blocks stored, then the region server writes one copy, one replica of every block to the same machine. So it is a physical hard drive on the same machine as the region server. And of course, there's also 2 more replicas of the block somewhere else, but there is a local copy. Now, what's very powerful is that the region server, when it reads back the data, is going to directly read it from the local drive. That's called short-circuiting. And it's possible because the people who design HBase and HDFS are the same people, so they can kind of cheat, right? And so the region server, when it wants to read back the data, has the knowledge that there is a copy of that data locally. It doesn't even need to go through the name node or whatever. It can cheat and directly reads it locally from the disk. And you agree that reading locally from the local drive is much faster than going through all the HDFS architecture. Who sees that? Right? That's called short-circuiting. And that's one of the other secrets why it's actually fast, why HBase is actually fast. So this is also a concept called locality, just like in physics. It's local because we have a copy of the data on the same machine as where it was written from. However, with time, as things evolve, and that's a little bit like quantum physics when the wave function starts spreading, at some point, because of some load balancing in HDFS, after a while, some blocks might no longer be there or might be offloaded somewhere else. And so it seems like we start losing that benefit because then we have to read via HDFS from other machines. So it seems that we are losing that over time. However, you remember that after we have flushed, we will compact. And when we compact, we again write a completely new file to HDFS. That is the compacted file obtained from the previous ones. And because when we compact, we write a new file, we again write from the region server to the data node, and it's again the same machine. So the new H file that is compacted from the previous one will again be on the same machine. So you see, it's magic. Every time you flush, every time you compact, you bring back all of the data, a copy of the data on the same machine. The same goes when a region switches the region server. If the H master says, now this region is no longer handled by you, it's now handled by this different region server. Then at first, the new region server might not have the data locally because that was written by another region server. So the new region server might be a bit slower at first because it needs to read from somewhere else. But the new region server at some point will do a compaction. And when it does that compaction, it again brings back a copy of the data on the same machine. Right? So that's an additional benefit of flushing, compacting, flushing, compacting. Every time you do that, you bring back a copy of the data on the same machine as the region server. And that's very efficient. Right? Who is with me? Right? So now you probably are connecting the dots with what I told you 2 weeks ago on the importance that an HDFS client writes a copy of every block on the same machine as the machine on which it is sitting. That is why it works. Any questions?
Yes.
Yeah.
Yes. Cedric asks on Zoom, so is the data physically only stored in blocks through the data nodes?
Yes, absolutely, because the H file is an HDFS file. And an HDFS file is always stored as 128 megabyte blocks. So this is absolutely true. And there is a copy of each one of these 128 megabyte blocks locally on the same machine, plus 2 other copies at other places.
Yeah. This is also what Cedric follow up. Yes,
Yep.
that match. Yeah.
Yeah, thank you. Any other questions? Yes? Yeah. So this is a bit advanced. I can say a few words, but I don't want to confuse too much. In HDFS, when you have used the system for a very long time, at some points, it will be off balance. It might be that it's what I called hotspots earlier, right? It might be that there are places where there's been a lot of writes, and so there's going to be a lot of blocks on some of the data nodes, and some other data nodes might have less blocks, maybe because people did not write so much data to them. And so at some point, you might have an imbalance in your HDFS cluster. When there is an imbalance like that, there exists a way, it's optional, it's basically the system administrator who can run these things, but there is a utility that looks at the imbalance and restores a balance. So it's going to basically notice, okay, this data node has less blocks than the others, And so this tool is going to transfer some of the blocks to the data nodes that have less from the data nodes that have more. And the goal is to, again, balance the blocks over the cluster. But when you do that, that might lead to some blocks moving around after a while. And so you're going to no longer have them on the same machine again. But this is going to be solved the next time you flush or compact. Does it answer your question? Yeah, awesome. Yes?
Yes, a follow-up from Cedric. So in the key value model, actually the value is only a sort of pointer pointing to the right block.
No. So you mean the key values of HBase, right?
I think so.
The value is the actual value. It might be an XML file, a JSON file, or whatever. This is the actual data that you have in your cell. It might be 10 megabytes if it's a JSON or XML file. Waiting for a confirmation.
Yeah, but didn't we say it's stored as a block? I think this is about what actually being stored at the model.
So you mean H blocks, right? Just to make sure. Not an HGFS block, but an H block in HBase.
Yeah, blocked through the data node. That was from the previous question.
So you do mean HGFS block then?
Yes.
Yeah, but the HGFS block is just what contains the contents of the H file, right? So it's just bits. And then it's if you know what an H file is made of, that you know that there's actually key values in there. Does it make sense, or you need another explanation?
Kind of.
Kind of. Maybe you can ask on the forum, on the discussion forum, and we can take it offline. I can give more details.
Yeah.
Yeah.
Sure.
Okay. All right. I think there are no more questions. So now there's a bonus part that is not really part of the material, but I'm just showing to you because that's actually super cool. It's an evolution of HBase and HDFS. So HDFS and HBase, they are very widely used by companies all over the world. But Google actually already moved on to new technologies. They are no longer using this because they have found something even better. And that something better is called Colossus. That is the new HDFS. Or it was called GFS at Google. HDFS is the open source version, right? Google File System, GFS was the Google version. But they no longer do that. They use something called Colossus. Colossus is an improvement over HDFS because HDFS is on a single cluster at a single data center. Colossus is worldwide. So imagine now a worldwide service, just like S3, but that has an HDFS taste with a whole file system and namespace and block worldwide. And there's a lot of benefits that they get from this is that they solve a lot of problems that HDFS had. You remember that in HDFS, one of the problems was that the name node is a central point of failure, right? When the name node fails, we have problems, and there's been all kinds of ways to attempt to fix that with the secondary name nodes, the backup name nodes, all of these that I explained to you about. But it's not quite satisfactory because that remains a bottleneck and a single point of failure. And so in Colossus, what Google does is that instead of storing the metadata of the file system on something like the name node, they store it, guess what, in Bigtable, in HBase. So they use Bigtable or HBase. So Bigtable is just the Google version of HBase. So they put the information about which file contains which blocks, where the blocks are, and so on, in an HBase or Bigtable table, right? And in fact, that should remind you of the meta table because that's the same trick here. We also store the information about which region server handles which server on a special table to offload the HMaster that no longer has to deal with that. They did exactly the same thing. So they replaced they moved it from the name node to a Bigtable /HBase table. So the other improvement is that it's worldwide. So now they can replicate across regions of the world. It means that even if there's an earthquake or some very big catastrophe somewhere, then the data is not lost because there's copies at other places. So these are some of the improvements. And they didn't stop there. So not just Colossus to be the next generation of HDFS or GFS, they also replaced Bigtable or HBase with a new system. And that new system is called Spanner. Spanner is a gigantic worldwide HBase, not just a single cluster, but the whole world. And so they slightly adapted the data model in a couple of ways. So for example, now instead of just a row ID, you can have a multiple column row ID. So the primary key can now be on multiple columns. And the second thing they did is that the regions do not need to be contiguous, right? In HBase, a region is an interval, but now it's no longer an interval. And they call that a tablet. And a tablet can be the union of several regions, right? The reason they do that is that it gives them more freedom in balancing the workloads and making it efficient, right? So these are the two things they modified in there. And now there's so many zeros in there that I need to pause and actually count them. So this is 1,000, million, billion, trillion, trillions of rows. This is absolutely gigantic. And what's even super cool, it feels like a James Bond movie, like you know, the villain. We have a universe master that basically synchronizes all of the local clusters that are spread all over the world in America, Europe, Asia, Africa, Australia, like all over the place. And the data is a worldwide service, right? So this is what they are actually using, and that's an exabyte scale system that they build. And now it's you know, not just thousands of computers. Now we have hundreds of data centers that are glued in this way to the storage. So this is very large scales, and that means we now have millions, tens of millions of machines in our system, right? So yeah, that's basically what I wanted to show. It's not material, it's not part of the material, but I just wanted to show you the evolution of how to take that to an even larger scale, right? Yes? I'm not aware of any, it might be, but I think that there's a difference between HBase and HDFS and Colossus and Spanner, is that I don't know if there are many people who are interested in an open source version of an exabyte scale system, just because it's only very large companies or very large corporations that would need that kind of scale. So this is probably the reason why there's maybe less of an open source interest, whereas HDFS and HBase, that's the scale of one cluster, and that can interest a lot of companies who can set up their own cluster. But I should check, actually, we could check if there's actually an open source version of Colossus and Spanner. That would actually be interesting. Any other questions? All right, I will just check before you go. To see, oh, how you followed. Knowing that if there's any open questions, anything you didn't understand, we can take it to the internet forum. You can also write us emails to the TA team, to me. We can give you all the precisions that you need on anything that wouldn't be clear. But I just want to get the temperature here of
in the meantime, maybe a question on Zoom. Maximilian asked, does Google new system nowadays still use MapReduce or other processing paradigm?
So I don't know if it's still called MapReduce or if they still use MapReduce, but maybe I can add one item of information, is that one of the paradigms behind Colossus and Spanner is that they decoupled compute and storage. So we'll see that in the case of HDFS MapReduce, as we do it in this lecture and as most companies do it, we collocate compute and storage, meaning that we do the computations on the same machine as the data is stored, right? Just like we have the region servers on the same machines as the data nodes. But when Google went for Colossus and Spanner, they decoupled the two, and it is no longer the case for that architecture of Colossus and Spanner. It's no longer the case that you do the computations on the same machines as the data is stored, because they managed to find a way to keep it efficient based on the fact that it's replicated in worldwide locations and so on. So even if it's not on the same machine, the access patterns are still optimized, right? Does that answer your question? Zoom? Yeah, awesome. So now I'm happy because there's still a majority of 80%. I'm not surprised by the fact that there's between 50 and 79%, because this is the most difficult lecture of the entire semester, right? And you've made it, you've survived it, right? So this is why I'm absolutely not surprised. Do not hesitate to ask questions. Again, send us emails, write to the forum, read the textbook where it's again explained, and really ask us. And then we will make sure to help you understand everything. So this is it. Thank you very much. Thank you, Zikai, for moderating. Enjoy your exercise session and the quiz of the week. We are here for you if you need anything. And as for me, I'll see you next week at 8 a.m., same room, same day. Goodbye. Have a good day.